So we have already gone from polar coordinates to rectangular coordinates. Now we want to go the other direction. So if I have some coordinate in space on a rectangular coordinate system, in other words, x's and y's, I want to be able to turn that into something with r's and thetas. Well, fortunately, geometry is a prereq for precalculus, so we can think about that red point in space as defining a right triangle. The reason the right triangle is helpful is that that y-coordinate is now a side on the right triangle. That x-coordinate is also a side length on the right triangle. So if I want to find r, that's just a Pythagorean theorem problem. So we can find that r using Pythagorean theorem. We can also find theta using some geometry tricks here. Note that our y, well, that's just an opposite side on that right triangle, and x is an adjacent, so we can use one of our trig ratios. I recommend tangent, but you could use cotangent if you're feeling froggy. Since we're trying to find an angle, we want tangent inverse, y is our opposite, and x is our adjacent. So there's a bit more work required going rectangular to polar than there was for polar to rectangular. The other thing we want to be careful with is the inverse business here. We do want to double check that our points are actually going to match up. Because when we're talking about inverses, we get that domain range issue. We do want to double check that our quadrants match when we start with rectangular and move to polar. So we take a look at number 7 here. We have an xy. We have an xy coordinate pair, and we want to change that into a polar coordinate. So let's do it. R is the square root of x squared plus y squared. And theta will be tan inverse of y over x. Lots of parentheses. All right. So you can pick which one of these you want to tackle first. I'm just going to move from the right to the left. That was silly. I'm going to move from the left to the right. So taking a look at this Pythagorean theorem set up here on the left, I have a 2 squared. That's 4. And then I have a 2 root 3 squared. Well, 2 times 2 is 4. Root 3 times root 3 is 3. So we have a 4 times 3, which is 12. 4 plus 12 will be 16, and the square root of 16 is 4. Jumping over to this angle, this is where we want to be careful. If I take a look at tan inverse of 2 root 3 over 2, okay, those 2's cancel. I'm left with just that root 3. So jumping over to my unit circle here, if you just Google the word unit circle and then include the word tangent in that unit circle search, note that you will find unit circles that have tangent values already calculated. That's often nice. But we actually see root 3 twice on the unit circle. Keep in mind a calculator will only give you that first quadrant angle, but there are 2 places where tangent is root 3. So we do want to double check. I started with an x coordinate of 2 and a y coordinate of 2 root 3. This is a quadrant 1. This is a quadrant 1 point. So using my unit circle, I'm going to pick this quadrant 1 theta. If you chose to pick this quadrant 3 theta, what is it here, 4 pi over 3, you're not wrong, but you would have to do a little bit of work. Remember, polar coordinates are not unique. So the one that I would like, tangent inverse of root 3 is pi over 3. So this is the one that I would like. But keep in mind, you could say negative 4 pi over 3. That's what we were playing around with last week. If you have angles that are 180 degrees apart, you can wind up with the same point. You just need to change the sign of your r value. So just kind of a weirdness that shows up with polar coordinates there. You could have done this using this angle as well. Taking a look at one more of these. Let's look at number 8 here. Notice now I'm talking about a quadrant 4 angle. You can tell it's quadrant 4 because of that negative sign right there in the y coordinate. So I have a positive x value and a negative y value. So let's go ahead and set that one up. This is going to be pretty ugly as far as that quadratic formula is concerned. So my x coordinates and y coordinates, squaring both of them. Squared plus negative 3 root 2 over 2 quantity squared. And then I have tan inverse. Now, take a look at what we're about to do. 3 root 2 over 2, over 3 root 2 over 2. One of them's positive, the other one's negative. So that is going to reduce to a negative 1. I'm trying to save myself a little bit of writing there. I'm also short a parentheses. I swear it's there. All right. It's this Pythagorean theorem business that's a little bit gross. So 3 root 2 over 2, note that that happens twice. So we've got a 3 squared, that's a 9. Root 2 times root 2, that's 2. So we're going to have that 9 times a 2, which is 18, over 2 squared, which is 4. And there are 2 of those. Save myself a little bit of room here. So we have 18 fourths plus 18 fourths. If you're concerned about the sign there, remember that I was squaring a negative, so it did become positive. So now we have 18 fourths plus 18 fourths, which is 36 fourths. That's nice because 36 is a perfect square. So the square root of 36 is 6. And the square root of 4 is 2. So hopefully our R value is just 3. Let's jump over to this tangent inverse business. That's going to be much quicker to deal with because we've already done that simplifying. Jump back to our unit circle. So where is tangent inverse going to be negative 1? Keep in mind there will be more than one of these. Here's one, and here's another one. So this was a quadrant 4 point in rectangular coordinates. So I'm going to pick the quadrant 4 angle. Keep in mind, you could pick that quadrant 2 angle, then you just need to deal with a negative radius. It's not the end of the world, but it's probably nicer to stick with this one here so you don't accidentally mess up that negative sign. So I'm going to bring that work all the way down here. That was 7 pi over 4. So there we have it. At this point, we have 2 examples going from rectangular to polar. Just like going from polar to rectangular, I will post some other examples. I'll just make subsequent videos there. It might actually be worth watching them for this. This is a more difficult task algebraically than going from polar to rectangular. Alrighty. See you soon.